Well, hello everyone, and welcome to the second lecture in the Inorganic Chemistry series for Chemical Science, SE5014. And this then continues our journey of or through the periodic table. So we move right across the periodic table and reach group 2, or the alkaline earth metals. That's beryllium, magnesium, calcium, strontium, barium, and radium. And in some respects, the relationships among the elements within this group are very similar to the relationships among the elements in group 1, or the alkali metals. Beryllium stands out slightly from the group because it tends to crystallize in slightly different structures to the rest of the group. And it doesn't form things like peroxides, unlike the rest of the group. And we'll see that as we progress through this lecture. But also there are some strange things going on in terms of melting points, boiling points, and atomization energies for these elements, which kind of sets them aside from their neighbours in group 1, where we see very defined trends as you proceed down the group. Radium is radioactive and is formed in the uranium decay series, and very much unlike francium, which sits at the bottom of group 1, it has a relatively long half-life. So 226 radium has a half-life of about 1,600 years. And it was discovered, extracted and purified by Marie Curie. And of course, you will all know the broad application that it found in cancer treatment, but that has now been largely superseded by other radioisotopes. So we will focus our discussion on beryllium, magnesium, calcium, strontium, and barium, and we can save the consideration of radioactivity until the final year in organic chemistry course. In terms of occurrence then, a very quick note on occurrence. Beryllium occurs mainly as the silicate mineral beryl, and emerald is a good example of that. Magnesium and calcium are very abundant in the Earth's crust, and also along with sodium and sodium chloride, magnesium, calcium, strontium and barium are very sort of widely distributed in minerals and found in seawater. And indeed, you get these beautiful tens of meters long crystals of gypsum, which is a calcium containing mineral, in Mexico. And there's a picture there of the Cueva de los Cristales in Mexico. Dolomite contains calcium carbonate and magnesium carbonate. You can get magnesite, which is a carbonate of magnesium, strontianite, which is a carbonate of strontium, and barytes, which is a sulfate of barium. Really, the only one of the elements within this group to be manufactured on a large scale, and really manufactured on an economically viable scale, is magnesium, and that is manufactured via the pigeon process. And it's based on what's called a silicothermic reduction of magnesium oxide. So what you do is you take dolomite, which contains both magnesium and calcium carbonate, and you mix that up with a ferrosilicon compound in the form of briquettes, a bit like, you know, the shape of the things you put on your barbecue. And you heat that up to very high temperatures, around about 1500 Kelvin. The magnesium and calcium carbonate are reduced to form magnesium oxide and calcium oxide, and they react with the ferrosilicon compound, and a product of that reaction is pure magnesium. And what happens then is that vaporized magnesium is water cooled, and you yield very pure magnesium. And the reason why the magnesium is so pure is because the vapor that comes off of that has a very low concentration of the other elements found in that reaction, such as calcium, iron, and silicon. Now, in exactly the same way as we saw sodium being extracted in the Downs process, you can also do exactly the same with magnesium. So you can also obtain magnesium from seawater. You can obtain beryllium from beryl by heating it with Na2SiF6, and you extract a water-soluble beryllium fluoride, and you can precipitate that out as beryllium hydroxide. And again, the production of calcium is through the electrolysis of fused calcium chloride and calcium fluoride. Now, beryllium is being right at the top of the group, of group 2. It's one of the lightest metals that's known, and this was exactly the same as lithium in group 1. Beryllium is non-magnetic. It has a high thermal conductivity. It has a super high melting point, and it's inert towards aerial oxidation because a very thin protective layer of beryllium oxide tends to form on the surface, and that protects the bulk material from oxidation. So just like some of the group 1 metals, you tend to find them in situations whereby light metals are required. So you can see some examples of their uses here. They are used in body parts, or sorry, beryllium is used in body parts in high-speed aircraft and missiles. It's used in communication satellites. Because of its high thermal conductivity, it's used in computer chip heat sinks. And one interesting application is it is born out of its lack of ability to absorb electromagnetic radiation. So you find that it doesn't really absorb X-rays that well, and that's because it has quite a low or very low electron density. So you'll remember from our discussions about X-ray diffraction in the first year that X-rays interact with matter through the electron cloud of an atom. And beryllium has quite a low electron density, so X-rays don't really interact with it or aren't really diffracted or scattered by it. So you tend to find it used in windows or tubes for taking X-ray diffraction or scattering measurements. Because if you have a protein or a crystalline compound that you're measuring with X-ray diffraction, you can put it in a beryllium tube, and the only thing that diffracts or scatters those X-rays is your crystalline compound and not the beryllium tube with its relatively low electron density. Magnesium is quite heavily used in the aerospace industry because it's used for reducing TiCl4 to produce titanium metal. And from 2010 to 14, there was a huge increase in the use of magnesium for this purpose. And the new, sort of relatively new Boeing 787 Dreamliner contains large amounts of titanium that have been produced using magnesium for reduction. You'll note then that it's quite heavily alloyed with aluminium. Well, that's very similar to lithium in group 1. And any sort of magnesium aluminium alloys have a high mechanical strength, but also have that corrosion resistance, which is important for things like the aerospace industry and the automobile industry. They're used in fireworks because when you ignite them, they produce nice colours. And magnesium is also used in indigestion powders. So milk of magnesia is essentially just magnesium hydroxide. And they're also used in Epsom salts, which is a magnesium sulfate-based compound. And you might put Epsom salts in your bath. Good for the muscles. Calcium metal doesn't really tend to be used for that much, but its compounds are used very heavily. And look at the large number of, well, calcium and magnesium compounds there really, but we'll focus on the calcium compounds. A large number of them are used, and that figure there of 296,000 megatons comes from 2008. So a serious volume of calcium-containing compounds are used annually. And of course, most of that is used in the building industry because the calcium oxide that is produced by calcining limestone is is used heavily in the building industry, and it's used in building mortar. You can very easily transport dry sand and calcium oxide because they're solid powders. And the moment you add water, the chemistry of that system leads to the mortar setting as solid calcium carbonate, and you use sand as the binding agent. So there's the chemistry of mortar and cement there. Now, calcium is used in the desulfurization process. So by that I mean the desulfurization of the combustion of fossil fuels, or the combustion products of fossil fuels. And both calcium carbonate and calcium hydroxide are used. So these compounds also have quite a heavy environmental significance. Now, of course, many of you will have learned about or studied, perhaps in secondary school, the problems that are associated with burning largely coal, and the fact that coal contains sulfur. And of course, when you burn it, it oxidizes to sulfur dioxide and enters the atmosphere, reacts with hydrogen in the atmosphere, and produces sulfuric acid. And of course, that then rains down on things like trees and plants, and it kills them. So it's really important that when we burn fossil fuels, and of course, unfortunately, we still are burning fossil fuels, but when we do burn them, the combustion products that are produced are desulfurized, and you can use calcium hydroxide and calcium carbonate to neutralize the sulfuric acid that's produced in these processes. So you can see there that calcium hydroxide and calcium carbonate will react with sulfuric acid to produce calcium sulfate. Of course, then that takes the sulfuric acid out of the environment. Drax Power Station in the United Kingdom operates 6 boilers, and it generates a relatively quite a significant proportion of the UK's required electricity at about 7%. And the coal that it burns has around about 2% sulfur. So you can do a bit of sort of back of the envelope calculations with that. The power station itself burns about 6,300 tons of coal a day. That equates to about 126 tons of sulfur, which of course oxidizes to sulfur dioxide, which is the real problem compound. And all of the chimneys at Drax Power Station have been fitted with limestone absorbers, so they all contain calcium carbonate. And the reactions that you can see below there remove about 90% of the sulfur dioxide that's produced. So on a yearly basis, around about 280,000 tons of sulfur are removed from the atmosphere. Strontium and barium then. Strontium used to find a very large application in the faceplate glass of colour televisions, because it blocked X-ray emissions from the cathode ray tubes. And I doubt any of you can remember the kinds of TV on the left there. I'm not even sure that I'm old enough to remember those kinds of televisions. But of course, nowadays we use flat screen televisions, whether that be LCD or LED, and the need for something that absorbs X-rays is completely gone. Barium is largely used as a weighting material in the oil and gas drilling industry. It does have medical applications in the form of its sulfate. So you might have heard people, or you might have seen on television, people having a barium mill before they have an X-ray. And what happens here is that a patient swallows a tablet of barium sulfate because it stops the passage of X-rays and makes it possible to image the gastrointestinal tract. Whereas usually, you know, the X-rays are only stopped by bone. It's very difficult to image soft tissue with X-rays. So you need to swallow something that interacts with these X-rays. Now, you can see there that the atomic radius increases down the group. I'm not going to go into the detailed explanation of why this is, because we spoke about that in lecture 1. And indeed, the trends are very similar to the group 1 metals. And similarly, the first ionization energy of the metals falls as you go down the group. And again, we spoke about that in lecture 1 when we were talking about the group 1 metals. Similarly, the electronegativity decreases as you move down the group. But what I really want to get onto is a consideration of the melting point, the boiling point, and the atomization energy of the group 2 metals. Because if you look at these graphs, you can see that the trends aren't really there. There's a broad decrease in melting point as you go down the group, but there's a strange irregularity between magnesium and calcium. It's very difficult to find any kind of meaningful trend in the consideration of boiling point as you move down the group. And again, there's no real pattern where atomization energy is concerned. And just a reminder there that atomization energy is the energy that's required to produce 1 mole of atoms in the gas phase from the element in its standard state. Now, if you compare this with what we saw in the last lecture for the group 1 metals, where we had a very consistent trend for melting point, boiling point, and atomization energy, this is completely different. And of course, all we've done is move one group right in the periodic table. So the question is, why do we not see consistent trends in these 3 properties in group 2 like we do in group 1? Let's begin with a slightly unsatisfactory explanation, because that's what the current explanation is. It's somewhat unsatisfactory. Let's begin by considering the melting point. And you can see that in the green box at the top right of this slide. Broadly, the melting point decreases as you go down the group. But we hit this slight irregularity when we get to calcium. Suddenly, the boiling point increases from 600 degrees Celsius in the case of magnesium, right the way up to 800 degrees Celsius in the case of calcium. Now, we can explain a broad decrease in melting point as you go down the group by considering the strength of the metallic bonds as you go down the group. And we spoke about this last week when discussing the group 1 metals. That metallic bond becomes weaker as you go down the group. And we explained that by a very simple proximity argument and a very simple model of metallic bonding. And we said that as you go down the group, the atoms get larger and the nuclei become further away, and therefore they are farther away from the delocalized electrons, or the sea of delocalized electrons that forms the simple model of our metallic bond. And the attractive forces that hold the metal together as you go down the group therefore decrease. And it's much more easy to separate the atoms to form a gas. Now, we now know that there's no real simple decrease in melting point as you go down the group because we've got this irregularity. So what's going on? Well, one explanation is that there is a crystal structure change as you go down the group. So beryllium and magnesium tend to adopt a hexagonally close packed structure. Calcium and strontium adopt a face-centered cubic structure, and barium adopts a body-centered cubic structure. So the question there is, could that change in crystal structure in going from magnesium to calcium, from a hexagonally close packed to a face-centered cubic crystal structure, could that account for this somewhat anomalous melting point value? But there's an issue with that explanation. If you think about it logically, there's an issue because there are 3 crystal structure changes as you go down the group. If there was just one crystal structure change between magnesium and calcium, it might be easily explained. But let's focus on that first crystal structure change, which occurs between magnesium and calcium from a HCP to an FCC structure. A hexagonally close packed and a face-centered cubic crystal structure are both 12 coordinate crystal structures. That means that every atom within that crystal is surrounded by 12 other atoms. And in that case, the metallic bond should be quite similar because atomic orbital overlap will be exactly the same, and electrons will delocalize in a fairly consistent manner between those 2 crystal structures. Barium then adopts a body-centered cubic crystal structure, which is an 8-coordinate system, and it's a far less efficient packing system, and we would expect the metallic bond between barium atoms to be weaker than in a 12-coordinate system. But if you look, the difference between the melting points of strontium and barium in going from a 12-coordinate crystal structure to an 8-coordinate crystal structure is quite minimal. Barium has a lower melting point than strontium, but it's not dramatically lower. So if this argument were to stand up, then what we would see is that we would expect a large difference in melting point between strontium and barium, because it's even more of a drastic crystal structure change than the one between magnesium and calcium. So the conclusion really is that the change in crystal structure here as we go down the group doesn't provide a satisfactory explanation for changes in physical properties. Now, melting points are inherently quite inaccurate indicators of the strength of a metallic bond. And really, because the material is still in the liquid state, so metallic bonds still exist. Those metallic bonds, of course, only break when the metal boils, or and it becomes a gas. So we tend to use boiling point and atomization energy for indicators of the strength of a metallic bond, because in both of those cases we're considering the transition of free atoms into the gaseous state with that metallic bond completely broken. Now you can see, if you look at the atomization energy trends, then magnesium has the lowest atomization energy value, but there's not really an obvious trend, and of course the same is true for the boiling points. Now there's obviously something unique to the group 2 metals that causes this trend, but the actual answer is that there's not really any convincing explanation for why we gain this low melting point at magnesium, or indeed why we gain a seemingly random array of boiling points and atomization energies for the group 2 elements. So the kind of short, easy answer is that no one knows why this trend exists. And that fact always amazes me, because when you study chemistry at GCSE and A-level, I remember studying group trends and periodicity. And you're kind of always told that there are very distinct changes as you move either up or down the periodic table, or left or right through the periodic table, and that these trends are empirical and are easily worked out. But here's an example in the group 2 metals of where there is not really any solid trend in terms of melting point, boiling point, and atomization energy, and actually no one really understands why. brief note on their reactivity then. Beryllium and magnesium are what's called passivated and are kinetically inert to oxygen and water. So at ambient temperatures, what you get is a protective oxide coating on the top of the material, and the bulk material remains unoxidized. Magnesium, and you'll see this in the laboratory and may have seen this before in the laboratory, magnesium will react with steam or hot water, but it has to be at an elevated temperature. If you heat the group 2 metals, they all combine with oxygen, nitrogen, sulfur, or the halides. And certainly the calcium, strontium, and barium have very similar properties to sodium, but are less reactive than sodium. So they react with things like water and acids to liberate hydrogen. And similarly, all three react with liquid ammonia in exactly the same way as sodium. So they will generate that deep blue solution and free solvated electrons. And we studied that in the last lecture. Here's an example of where beryllium is slightly different to the rest of the group, because the anhydrous beryllium halides are all covalent structures. So beryllium fluoride crystallizes with this beta cristobalite structure, and beryllium chloride at high temperatures exists in a monomeric and dimeric form. But if you crystallize it out in the solid state, then it forms these deliquescent crystals, which contain infinite chains of tetrahedrally coordinated beryllium. As you move down the group, then the halides become more ionic in character. So the fluorides of magnesium, calcium, strontium, and barium are all ionic. They've all got pretty high melting points, and they're not very soluble in water. And you might want to sit down and predict why that is based on the thermodynamic considerations that we were talking about last time in terms of solubility. One area that is of quite intense theoretical interest at the moment is the structures of the gaseous group 2 metal fluoride and later halide molecules. So things like beryllium fluoride, chloride, bromide, and iodide, right the way down to barium fluoride, chloride, bromide, and iodide. And as I said, there's a lot of interest in these in the sort of theoretical chemistry literature. Before we proceed with considering these, I just want to define what we mean by quasi-linear. Quasi-linearity is when a molecule exhibits very little difference in terms of energy between a linear and a bent structure. So for these very simple molecules in the gas phase, they've got 3 atoms in them, 1 group 2 metal atom and 2 halide atoms. So they can be linear or bent, but if the calculated energy difference between the linear and the bent structures is less than 4 kilojoules per mole, i.e. essentially indistinguishable, even by measuring using modern techniques, then we denote them as quasi-linear. So using that definition, you arrive at the structures given in the table on the left there. So these are all products from theoretical calculations. And you can see that there is a general preference for a bent structure when you have a heavier group 2 metal with either fluorine, chlorine, or bromine. If you stick at the top of the group with the lighter metals, then you see that the structure of these molecules is linear. And there's a lot of debate in the literature, and if you go away and you read any of the literature surrounding this, there are lots of theoretical studies into the structures of these compounds in the gas state. Then you see that there's a lot of disagreement and debate as to whether or not either of those molecules should be classed as bent, quasi-linear, or linear. And there are kind of 2 major explanations for this in the literature, and two approaches which are used when calculating the structure of these molecules, or the energetics of the structure of these molecules. One is is a theory surrounding inverse polarization, and the other is a theory surrounding the potential for the participation of d atomic orbitals in the heavier elements. So we'll deal with inverse polarization first. If you've got a metal ion and it is polarizable, then it will be polarized by something like a fluoride or a chloride anion. So what's happening here is that one of those fluoride ions is approaching a metal, and because of its large electron cloud, it's essentially forcing the electrons in the metal over to one side of the atom. What's found, or what's predicted using the inverse polarization theory, is that that bending increases when you've got an increase in the polarizability of the metal ion. And remember that the electrons, as you move down the group, are becoming further and further away from the nucleus. So they're much more easily polarized, or the atom is much more easily polarized. So because of that polarizability, then you get a bent structure. Now there is another explanation or another theory, and that's that maybe the d atomic orbitals are participating in bonding. And you'll remember the structure of the d orbitals from our studies of crystal field theory last year. Magnesium and beryllium then only have s and p orbitals, and the best overlap between the metal and the halide then is through a straight linear overlap. Whereas calcium, strontium and barium have vacant 3d, 4d and 5d orbitals, and they are available for participation in bonding, and they can only overlap efficiently if the orbitals on the x atoms are in that bent conformation. Now, of course, the obvious answer then, or the obvious conclusion, is that actually, you look at the literature now, it's likely that it may be a combination of both approaches. So in fact, inverse polarization and the participation of the d orbitals might contribute to the shapes of these molecules. So just to talk about the oxides and the peroxides, beryllium oxide is formed by ignition of beryllium or its compounds in oxygen. And it's an insoluble white solid, and it adopts this wurtzite structure. So again, there's an example of beryllium kind of going it alone and needing to be different. The oxides of all the other group 2 metals are usually prepared by the thermal decomposition of the corresponding carbonate, and they all crystallize with the sodium chloride structure. If you look at the trends in the melting points of the oxides, well, we know that magnesium, calcium, strontium and barium oxide all have that consistent sodium chloride structure. So we see a decrease in the melting point as we go down the group for their oxides. And we can look at the stability of the group 2 oxides through consideration of the lattice energy. And I'll use a slightly different definition of lattice energy as when compared to what I was talking about in the first lecture. You'll note that my lattice energy here has a negative sign in front of it. So this is the exothermic value for the lattice energy, delta H lattice. And it's negative because we are now considering what happens when atoms coalesce from the gaseous state in a vacuum to form an ionic lattice. And of course, when they do that, there's a huge release of energy. You'll notice then that the lattice energy in going from magnesium through to calcium down to strontium oxide becomes less negative as you go down the group. What that tells you then is that magnesium oxide is in fact more stable than strontium oxide by around about 700 kilojoules per mole. And that makes sense because the cations are much smaller at the top of the group, meaning that they can get closer together, and those attractive forces that hold the lattice together are much stronger. You can form group 2 metal peroxides, so MO2, for magnesium, calcium, strontium and barium. And again, in the literature, you'll find people trying to prepare beryllium oxide, but attempts to do that have so far failed. The peroxides of the group 2 metals will very easily decompose into their respective oxides, and the extent to which that happens can be predicted based on the lattice energy of the oxide and the peroxide. You can see there, for example, that the difference between the lattice energy of magnesium oxide and magnesium peroxide is about 400 kilojoules per mole. And because the difference is very large, we would predict that if you had the peroxide out on the bench, it would convert back into the oxide. And you'll note then the difference between strontium oxide and strontium peroxide is much smaller. So because that difference in lattice energy is smaller, we would predict that the peroxide is relatively stable with respect to the oxide. The peroxide is always less stable than the oxide, however, and we can see that as by comparing the lattice energy of strontium oxide and strontium peroxide, and you'll note that marginally the lattice energy of the strontium oxide is more negative than the lattice energy of the peroxide. And of course, we can demonstrate that mathematically by using something called the volume-based thermodynamic approach. What that does is it relates the lattice energy to the inverse cube root of the volume of a unit cell. And we can calculate a value for the lattice energy. And if you want to see more information on the thermodynamics of the alkaline earth metal peroxides, then I urge you to read the two papers that I show you on the right there. Finally then, a little bit of coordination chemistry. There are a couple of important ligands that bind magnesium and calcium. Probably the most important is EDTA, and it's used as a sequestering agent to remove water and magnesium from very hard water. I think it's also used medically to remove metal ions from the body if you overdose on small metals. Magnesium, calcium, strontium, and barium will form complexes with the crown ethers, just like the group 1 metals do. And again, there's a correlation between the ionic radius of the group 2 metal cation and that internal cavity radius of the cyclic ligand. And finally, an important class of macrocyclic ligands are the porphyrins. And you can see that chlorophyll is an example of a porphyrin ligand that binds magnesium. And that extensive conjugated network that surrounds the magnesium is the result, or is why plants are green, essentially, because it absorbs light in the visible region. Okay, I will leave you there with some questions. We will have time to go over these in our face-to-face sessions, and thank you very much.